force in our first person. Charles Coulomb. Charles Coulomb is given credit because he really wanted to experiment with the amount of force that was created by two particles. When I'm thinking of particles, I want you to bring yourself back to chemistry. So we're thinking about electrons and protons. We've learned before that electrons have a negative charge, and they give you the specific number right around negative 1.6 times 10 to the negative 19th in your textbook. Electrons are negative, and your protons are going to be positive. And of course, neutrons are neutral. So when we're talking about charged particles, we're thinking about our electrons and our protons as well. Coulomb is also given credit for Coulomb's constant, which is represented by K. And it is 8.98 times 10 to the ninth. You should see the units Newton times meters squared divided by Coulomb squared. It reminds you that your distance still needs to be in meters. Force is always in newtons. And of course, we have that new unit, which is a Coulomb. This is Coulomb's law played out. We have force represented by capital F. Coulomb's constant, which will be your 8.98 times 10 to the ninth power. Q1 and Q2, this is the charge of your two particles, and R squared. You may think of R as representing radius, and that's kind of what it puts you in the mind of. We're also thinking about distance in general. Either way, no matter what number they give you, ensure that your units are in meters. Now, this looks really similar to an equation we've used before when we did universal gravitation. Instead of having K, we had capital G. Instead of having Q1 and Q2, you had M1 and M2. So if you think about it, we've pretty much gone through the bones of this type of problem. But let's look at an example. Here we have two stationary point charges of 6 times 10 to the 5th Coulomb exert a repulsive force on each other of 138 newtons. What is the distance between the two charges? This type of problem is going to ask that we actually rearrange our problem, which isn't an issue. We'll plug things in using the guess method and we'll kind of take it from there. So let's take a look at the information that we were given in the first place. We have two stationary point charges, and charges, remember, are represented by Q1 and Q2. So G is for my given. My Q1 will be 6 times 10 to the 5th. Pay attention to your units. You will often see the micro sign in front, so it could be a micro Coulomb. So make sure that you have a capital C alone. Q2 is also 6 times 10 to the 5th power. They also told us that we have a repulsive force of 138 newtons. So that will be equal to F. What is the distance between the two? So your unknown will be R. And our equation, it's the one that we just took a look at. Let's go up a little bit on the board just to give us enough room, because these problems can take up quite a bit of space. So F is going to equal K, Q1, Q2 divided by R squared. The easiest thing for us to do is to forget the square. So we're going to plug in the numbers that we have, and in the end, we'll notice a simple trick that will follow us throughout. For force, we have 138 newtons. There were no substitutions to make. For Coulomb's constant, we're going to use our 8.98 times 10 to the ninth power. We have our Q1 and Q2 are both the same. So 6 times 10 to the 5th. And that's divided by R squared. Now, if you've been with me for any number of time, you've heard me say that R squared and F simply switch places. So we're going to switch the places of those two, multiply through on the top, and see what we get. So we're going to move our R squared over. Grab your calculator. We'll do 8.98 times 10 to the ninth power. It's going to be multiplied by 6 times 10 to the 5th power times 6 times 10 to the 5th power. And that's going to leave me with 3.23 times 10 to the 21st power. I got this number here from simply multiplying straight across. And of course, our 138 will come to the bottom. Now, let's simplify here by dividing. And we end up with r squared equals 2.34 times 10 to the 19th power. Now, it's easy to stop here. And if you're taking a standardized test, this is exactly that first answer choice that they may offer you. But be careful. Math is in the numbers and math is in the units. You still have r squared. So we already know in order to get rid of the square, we will take the square root to find out exactly what the distance is in r. Take your square root of 2.34 times 10 to the 19th power. And don't forget that your exponent is important. And we end up with a number that needs to be in scientific notation. It gives us 4.83 times 10 to the 9th power. And distance is measured in meters. So we have our given information, our unknown, the equation of choice, and then from there, we're simply going step by step. As you're walking through, pay attention to where you are using your parentheses. Remember that calculators are all different, but they can definitely be finicky in between. Now that we've talked about the charge that can exist between two particles, let's look at another side of electricity altogether, which kind of brings us to a more broken down sense of exactly what's going on inside of that circuit that we're going to be investigating. This is an electric field. You guys have learned before that opposites attract. If we have a positive proton and negative electron, there's going to be attraction here. And you notice the connection of your field lines. But remember, positive thoughts should go out. Negative thoughts should also always stay with you. So arrows going in will show an item that's negative. Arrows going out will indicate a particle that's positive. It's not uncommon to receive a test question, and they will put the letter A and B here. And they'll simply ask you, please identify the positive object. Please identify the point that has a negative charge. So it's two ways of asking you which one is an electron and which one is a proton. The easiest way for us to figure that out is, of course, to use your arrows. Here's another example. If I have like charges, two positive protons or even two negative neutrons, if they are the same charge, they're going to repel. So I don't expect to see the connections in the middle. Field lines are really nice, and we'll visit these again when we talk about magnetism, and you can actually see those lines come together. Just keep in mind the charges that you've already learned before. Electric current, we're somewhere around page 596. Current is going to be measured in ampere, or we often shorten this to amps. And we'll talk about the scientists a little bit later who gave us or discovered currents. It's going to measure the rate at which electrical charges are going to pass through a given area. This current kind of reminds you almost of period. How much is flowing through in a particular amount of time? The equation we use for current is I equals Q divided by T. We already know that lowercase t indicates time. This Q is going to be your charge, just like Q1 and Q2 from our Coulomb's law equation. We're going to add something in new, which is the letter I, and we're using a capital I to represent current. Current is measured in amps. We have our charges that are measured in Coulomb. Time is still measured in seconds. Here's an example. Let's say the current in a wire of a CD player is 0.058 amps. How long would it take a 2 Coulomb of charge to pass through a cross-sectional area of wire? Really wordy, but the equation has already shown us that this particular problem is simple. So let's use our G for given. They told us that we have a CD player that has amperage of 0.058. So I equals current. And it also has a charge of 2.0. So that would be the letter Q. And Q is going to equal 2 Coulomb. Our unknown, how long would it take? So we're looking for time. The equation, I equals Q divided by T. Whenever we are looking for what is on the bottom, after checking that our units are correct, T and I will switch places. T equals Q divided by I. From here, plug in your numbers. Q is going to be 2. Here, our current is 0.058. Grab your calculators and let's figure out our specific number of seconds. .48 seconds is the answer. You're able to identify your given information, current, and your charge. We're looking for time, and we're going to use our equation for current. And we're looking pretty good, 34.48 seconds. Now, the other equation we're going to look at will be Ohm's law. And this equation is very straightforward as well. We like the smaller equations because they help us double check our larger equations. So Ohm's law is going to show the relationship between voltage, current, and resistance. You have a very good set of notes that should be attached to the email that also contain the link to this video. I encourage you to definitely go through the notes and the practice pages. There should be a total of 2 that will give you Ohm's law as well as break down the different styles or different setups. So if you are looking for current, we will use this equation, or resistance. Now, remember we've already defined voltage, current, and resistance before. It's on one of our earlier worksheets when we were introducing the electric house project. Take a look at this picture. You have volts, we have amperage, and remember current is measured in amps, and then we have ohm. Now, ohm is going to deal with the material that you're passing through. This is why I always ask the questions about conductors and insulators. If a material is a good conductor, it allows an easier flow of electrons. If it is an insulator, it will not allow a very smooth flow. Voltage is the push. How much push do you need? If you think about battery size, we've been working with 9-volt batteries. Compare that to a D-cell battery and then to a AAA battery. If I wanted to look at the D battery or the AAA, I have a larger expectation of that D battery simply based on the size. Amperage is your current, so how much is able to pass through at that time? Stare at this picture and be able to explain it because you'll definitely see it again. In this lesson, we had a chance to introduce you guys to current. We also talked about electric force and showed you electric fields. If you have any questions, always send me an email. If you would like more information or another way to look at these 2 lessons, I've attached 2 links for you as well. I'll see you guys in class.